Hey there. My name is Alara, and welcome to the Late Night Science Channel. Tonight, we're going somewhere truly special. You know that feeling when you look up at the night sky and everything just quiets down? That's where we're headed. So get comfortable. Maybe adjust your pillow. Let your breathing slow just a bit. And hey, if you enjoy these gentle journeys through space and science, go ahead and tap that like button. It really helps others find this peaceful corner of the internet. Subscribe too if you want more of these calm explorations, but no pressure. Just let's drift together into the cosmos. Right now, somewhere above you, light is traveling. Light that left distant stars before you were born, before your parents were born, maybe even before humans walked this earth. And it's finally arriving, right now, this very second. Isn't that something? The universe has this way of making you feel both incredibly small and somehow connected to everything. Tonight, we're going to explore that connection slowly, gently, letting each idea settle like snowflakes on a quiet winter evening. So here's something that might make your mind stretch a little. When you think about all the beaches on Earth, every grain of sand, millions and billions of them, right? Well, there are more stars in the universe than all of those grains combined. Just let that sink in for a moment. Each one of those stars, a blazing ball of light and energy, some bigger than anything we can imagine, some smaller, some hotter, some cooler, each one potentially surrounded by its own family of planets, moons, maybe even life. The sheer abundance of it all is almost overwhelming, but in a peaceful way, you know? It reminds us that we're part of something so vast, so rich with possibility, that our little worries here on Earth are just tiny ripples in an endless ocean of existence. And speaking of vast, the observable universe, the part we can actually see, stretches about 93 billion light years across. 93 billion. That's the distance light travels in 93 billion years. And light moves fast, really fast, about 186,000 miles every single second. But here's the thing. Here's what makes it even more mysterious. That 93 billion light years, that's just what we can observe. Beyond that boundary, there's probably more, maybe infinitely more, stretching on and on, filled with galaxies and stars and planets we'll never see because their light simply hasn't had enough time to reach us yet. Those distant realms exist in a kind of permanent darkness for us, forever hidden, forever unknown. It's like standing at the edge of a vast ocean at night, knowing there are islands out there you'll never visit, ships you'll never see. The universe keeps its secrets well. Now, here's where it gets even stranger, and I mean this in the most calming way possible. Space itself is expanding, not just the things in space moving apart, but space, the actual fabric of reality, is stretching. Imagine a balloon with dots drawn on its surface, and as you inflate the balloon, those dots move farther apart, not because they're traveling across the balloon, but because the surface itself is growing. That's what's happening to our universe. Right now, this very moment, galaxies are being carried away from each other by the expansion of space itself. It's slow, gradual, but relentless, like a tide that never stops. This cosmic growth affects everything, from how light travels across the void to what the universe's ultimate fate might be. And we're all just riding along on this expanding wave, passengers on a journey that started almost 14 billion years ago. And about that journey's beginning, about the Big Bang, you've probably heard it described as an explosion, like some massive firework going off in empty space. But that's not quite right. The Big Bang wasn't an explosion in space, it was the creation of space itself, and time too. Before that moment, there was no space to move through, no time passing by, just nothing. or maybe something so different from what we understand that our minds can't quite grasp it. Then suddenly, from a state of unimaginable density and heat, space began expanding and time started ticking forward. Everything, all the matter and energy, all the potential for stars and planets and life was contained in that first moment and then released into the growing universe. It's hard to wrap your head around, honestly, but that's part of what makes it so fascinating. The universe's beginning is as mysterious as its eventual end. There's this faint glow that fills the entire universe, every corner of space, called the cosmic microwave background. It's ancient light, the afterglow of the Big Bang, dating back almost 14 billion years. When the universe was very young, it was hot and dense, and light couldn't travel freely because it kept bouncing off charged particles. But as things cooled down, around 380,000 years after the beginning, the universe became transparent. Photons could finally travel without constantly scattering, and they've been streaming through space ever since. Today, that light has stretched and cooled into microwaves, invisible to our eyes, but detectable with sensitive instruments. This radiation is like a baby picture of the universe, showing us what things looked like when the cosmos was still in its infancy. Scientists study the tiny temperature fluctuations in this glow, variations of just a few millionths of a degree, because those ripples tell us how galaxies and large structures began to form. It's a silent messenger, surrounding us always, carrying stories from the dawn of time. Most of the universe's matter is invisible. Strange, right? About 85% of all matter is something called dark matter, which doesn't emit, absorb, or reflect light. We can't see it directly, can't touch it, can't capture it in a bottle. We only know it exists because of its gravitational effects. Galaxies spin too fast for the visible matter alone to hold them together. They should fly apart, but they don't. Something invisible is acting like cosmic glue, providing the extra mass needed to keep everything bound together. This dark matter forms an unseen framework throughout the universe, a hidden scaffold that shaped how galaxies formed and where they cluster. Astronomers map it by watching how its gravity bends light from distant objects, creating a sort of shadow portrait of this mysterious substance. Despite being invisible, dark matter plays a fundamental role in everything we see, guiding the architecture of the cosmos in ways we're only beginning to understand. And then there's dark energy, which is even stranger. While dark matter pulls things together with gravity, dark energy seems to push things apart. In the late 1990s, astronomers made a shocking discovery. They expected to find that the universe's expansion was slowing down over time due to gravity, but instead, they found it's speeding up. Something is counteracting gravity on the largest scales, causing galaxies to accelerate away from each other faster and faster. This mysterious force, dubbed dark energy, makes up about 70% of the universe's total energy content. We don't know what it is, where it comes from, or why it behaves this way. It's one of the biggest mysteries in all of science. Dark energy challenges everything we thought we understood about gravity and the structure of space and time. It's out there right now, gently pushing the universe to expand ever more rapidly, and we're just watching it happen, trying to figure out what it means for the future of everything. Galaxies aren't scattered randomly in space like seeds thrown in the wind. They're organized into an enormous cosmic web, a vast network of filaments and sheets made mostly of dark matter, stretching across hundreds of millions of light years. Along these filaments, galaxies cluster like beads on strings, connected by invisible threads of gravity. Between the filaments lie vast voids, enormous empty regions with very few galaxies, like cosmic deserts. This web structure influences how galaxies grow and interact, how they merge and evolve over billions of years. It's a delicate, sprawling network that reveals the universe's large-scale architecture. Though we can't see the dark matter directly, its gravitational pull shapes where galaxies form and how they move through space. Mapping this cosmic web helps scientists understand the universe's history and predict its future. We're all part of this web, our galaxy just one tiny node in an incomprehensibly vast network stretching across the observable universe. Our home galaxy, the Milky Way, is spinning through space at an incredible speed, over 500,000 miles per hour. That's fast enough to travel from Earth to the Moon in less than 30 seconds. And we're all along for the ride without feeling a thing. Our entire solar system orbits the galactic center, taking about 250 million years to complete one full orbit. Think about that. The last time we were at this point in our galactic journey, dinosaurs were just beginning to emerge on Earth. Since then, we've traveled around the galaxy once, witnessing countless changes on our planet, while the stars around us slowly shifted positions. Despite this dizzying speed, the distances between stars are so vast that collisions are extremely rare. We're all moving together in this grand cosmic dance, spinning through the galaxy's spiral arms amid clouds of gas and clusters of stars, part of something much larger than ourselves. Sometimes galaxies collide, not in violent crashes like cars on a highway, but in slow, graceful dances that unfold over billions of years. When two galaxies get close enough, their mutual gravity pulls them together, and they begin a cosmic waltz. Stars rarely collide directly because the distances between them are enormous, but the galaxy's shapes warp and change, spiral arms stretching and twisting. These encounters often trigger intense bursts of star formation as clouds of gas compress and collapse. The supermassive black holes at the centers of the galaxies may eventually merge, releasing tremendous energy. Our own Milky Way is on a collision course with our neighbor, the Andromeda Galaxy. In about 4 billion years, they'll merge into a single, larger galaxy. By then, our sun will be nearing the end of its life, but if anyone's around to watch, they'll witness one of the universe's most spectacular shows. Two galaxies slowly becoming one. Quasars are among the brightest objects in the universe, shining across billions of light years with incredible intensity. They're powered by supermassive black holes at the centers of young galaxies, black holes consuming enormous amounts of gas and dust. As matter spirals into these black holes, it heats up to millions of degrees, releasing tremendous energy across the electromagnetic spectrum. A single quasar can outshine its entire host galaxy, making it visible from unimaginable distances. Because light takes time to travel, when we observe quasars, we're seeing them as they were billions of years ago in the universe's youth. They serve as cosmic lighthouses, illuminating the conditions in the early universe and helping us understand how black holes grew and galaxies evolved. Their dazzling brightness and immense distance make them fascinating windows into cosmic history. In the universe's very first moments, something extraordinary happened. Within a tiny fraction of a second after the Big Bang, space itself expanded exponentially in an event called cosmic inflation. During this brief period, perhaps lasting only a trillionth of a trillionth of a trillionth of a second, the universe grew from smaller than an atom to macroscopic size, expanding faster than the speed of light. Now, nothing can travel through space faster than light, but space itself isn't bound by that rule. Inflation smoothed out irregularities in the early universe, making it remarkably uniform on large scales. It also stretched tiny quantum fluctuations, microscopic ripples, into the seeds that would eventually become galaxies and clusters. This rapid expansion solves several cosmic puzzles and is a cornerstone of modern cosmology. It's almost impossible to imagine something happening that quickly, but the evidence supports it, written in the patterns we see in the cosmic microwave background radiation. For hundreds of millions of years after the Big Bang, the universe was dark. No stars, no galaxies, just vast clouds of hydrogen and helium drifting through space. Then the first stars ignited, massive and brilliant, burning hotter and faster than most stars today. These ancient stars, sometimes called population 3 stars, lit up the cosmos for the first time, ending the cosmic dark ages. Their intense radiation began to ionize the surrounding hydrogen gas, transforming it from neutral atoms to plasma. This process made space transparent to ultraviolet light, allowing photons to travel freely. The first stars lived fast and died young, exploding as supernovae and scattering heavier elements into space. These elements, carbon, oxygen, iron, and others, became the building blocks for the next generation of stars, and eventually for planets and life. The era called Cosmic Dawn transformed the universe from a cold, dark void into a vibrant, light-filled expanse, setting the stage for everything we see today. High-energy particles called cosmic rays race through space at nearly the speed of light, flung outward by some of the universe's most violent events. Supernova explosions, colliding stars, energetic black holes. These phenomena accelerate protons and atomic nuclei to incredible speeds. Cosmic rays travel across the galaxy and sometimes reach Earth, where they collide with atoms in our atmosphere, creating showers of secondary particles. These energetic visitors can influence atmospheric chemistry and may even play a role in cloud formation and climate. Though invisible and mysterious, cosmic rays directly link us with the universe's most powerful events. Every second, trillions of them pass through your body without you noticing, tiny messengers from distant cosmic violence. They remind us that we're not isolated from the rest of the universe. We're constantly being touched by its energy, connected to events happening light years away. Our home galaxy, the Milky Way, isn't alone. It belongs to a massive structure called the Laniakea supercluster, which contains thousands of galaxies spread across hundreds of millions of light years. This colossal cosmic metropolis is a sprawling network of galaxies moving together through space, all influenced by the immense gravitational pull of the supercluster's dense regions. Within Laniakea, galaxies interact, collide, and grow, shaped by forces operating on scales almost beyond comprehension. Understanding our place within this vast community helps astronomers grasp the large-scale structure of the universe and the forces shaping it. We're part of something much bigger than just our galaxy, part of a cosmic family bound together by gravity, all flowing along currents defined by the distribution of matter throughout space. Between the dense clusters and filaments of galaxies lie enormous cosmic voids, vast regions with very few galaxies and low matter density. These voids can span tens of millions of light years, immense emptinesses where almost nothing exists. Though nearly empty, they contain sparse gas and dark matter, and they play an important role in shaping the universe's structure. Voids influence how galaxies move and cluster around them, carving out the cosmic web and affecting the dynamics of cosmic expansion. Studying these empty regions sheds light on fundamental cosmic mysteries like dark energy and matter distribution. They're like the silences between notes in music, defining the structure just as much as the clusters themselves. The universe is as much about emptiness as it is about matter and light. Neutrinos are tiny, nearly massless particles produced in vast numbers by the sun, exploding stars, and other cosmic events. These ghostly particles barely interact with matter, passing through entire planets without notice. Trillions of neutrinos fly through your body every second, connecting you to the energetic processes of the universe. Detecting them requires massive, sensitive instruments buried deep underground or under ice to shield them from other particles. Despite being elusive, neutrinos offer unique insights into stellar explosions, the sun's inner workings, and fundamental physics. They carry information from places light can't escape, like the cores of supernovae or the centers of stars, making them invaluable messengers from the cosmos's most extreme environments. When you look at the universe on the largest scales, across hundreds of millions of light years, it appears remarkably uniform. No matter which direction you look, the distribution of galaxies and matter shows no preferred orientation. This cosmic isotropy, paired with homogeneity, means the universe looks much the same everywhere. This principle underlies much of modern cosmology, simplifying our models of the universe's evolution. Observations of the cosmic microwave background radiation strongly support this large-scale uniformity, hinting at fundamental symmetries in nature. It's comforting, in a way, to know that the universe doesn't play favorites, that the laws of physics and the distribution of matter are consistent no matter where you are in the cosmos. Almost instantly after the Big Bang, the universe was flooded with neutrinos, those tiny particles we mentioned earlier. Within the first second, these neutrinos decoupled from other matter and have been streaming through space ever since, forming a cosmic neutrino background. Unlike light, these relic neutrinos pass through almost everything unimpeded, making them incredibly difficult to detect. Despite being elusive, neutrinos offer unique insights into stellar explosions, the inner workings of the sun, and fundamental physics. They carry information from places light can't escape, like the cores of supernovae or the centers of stars, making them invaluable messengers from the cosmos's most extreme environments. Scientists measure the universe's current expansion rate with something called the Hubble constant. This value links how fast galaxies are moving away from us to their distance, providing a cosmic speedometer. However, measuring the Hubble constant precisely has proven challenging, with different methods yielding slightly different results. This tension in measurements fuels ongoing research because knowing the exact rate helps us understand the universe's age, size, and ultimate fate. The Hubble constant is a fundamental parameter in cosmology, anchoring our understanding of cosmic history and expansion. It's one of those numbers that sounds simple but carries profound implications for everything we know about the universe. As galaxies move away from us, their light stretches to longer, redder wavelengths, a phenomenon called redshift. This is similar to the Doppler effect with sound, where a passing siren's pitch lowers as it moves away. Redshift not only tells us the universe is expanding, but also helps astronomers measure distances to faraway galaxies and look back in time. The farther away a galaxy is, the more its light is redshifted, meaning the faster it's receding. By analyzing redshift, scientists can piece together the history of cosmic expansion and understand how the universe evolved over billions of years. It's like the universe is leaving breadcrumbs, little clues in the light, telling us its story. Measuring vast cosmic distances requires clever techniques because objects are too far away to gauge with simple methods. Astronomers rely on the cosmic distance ladder, a series of interconnected methods, each building on the last. They start by measuring distances to nearby stars using parallax, the apparent shift in position when viewed from different points in Earth's orbit. Then they use standard candles, objects whose true brightness is known, like certain types of variable stars and supernovae, to estimate farther distances. This layered approach allows scientists to map the universe's vastness accurately, helping us understand the scale of cosmic structures and the timeline of the universe's evolution. Each rung on the ladder extends our reach a bit farther into space. Because the universe is about 13.8 billion years old, light from beyond a certain distance hasn't had time to reach us. This boundary, known as the cosmic horizon, defines the observable universe, the sphere around us containing everything visible. Beyond this horizon may lie countless more galaxies and mysteries, but they remain forever out of reach. As time passes, the horizon expands slightly, gradually unveiling more of the cosmos. Yet, the cosmic horizon reminds us of the limits to our knowledge, urging humility and wonder as we explore the universe. There's something both frustrating and beautiful about knowing there are places we'll never see, secrets we'll never uncover. It keeps the universe mysterious, keeps us curious. Cosmic dust consists of microscopic particles made from elements like carbon, silicon, and metals. Although these grains are incredibly small, they play an outsized role in the universe's life cycle. Within dense clouds of gas and dust, gravity pulls matter together, and dust helps cool these clouds by radiating heat, allowing them to collapse further. This process leads to the birth of new stars. Around young stars, dust grains collide and stick, gradually forming planets, moons, and other celestial bodies. Dust also provides surfaces for complex molecules to form, fostering the chemistry essential for life. Without these tiny grains, star and planet formation would be much more difficult. They're the universe's building blocks, small but essential. The earliest stars formed from primordial clouds composed almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. These stars, sometimes classified as population 3, were massive and burned hotter than most stars today, producing intense radiation. They lived brief, brilliant lives before exploding as supernovae, dispersing the first heavier elements into space. These heavier elements became the building blocks for subsequent generations of stars, planets, and eventually life. While none of these first stars remain today, their explosive deaths shaped the chemical complexity of the universe and set the stage for everything we observe now. We're all made from stardust, literally, from the remnants of ancient stars that lived and died billions of years ago. Many distant galaxies are cloaked in thick clouds of cosmic dust that block visible light, rendering them invisible to optical telescopes. However, this dust absorbs energy from intense star formation and re-emits it as infrared radiation. Observing these galaxies in infrared allows astronomers to peer through the dust and uncover regions of vigorous starbirth. These dusty star-forming galaxies provide crucial insights into galaxy evolution and the early universe's growth. By studying them, scientists gain a fuller picture of how stars and galaxies have evolved over billions of years. It's like having X-ray vision, seeing through the cosmic fog to reveal what's hidden underneath. Cosmic rays are fast-moving particles, mostly protons, accelerated by powerful cosmic events like supernovae and active galactic nuclei. When they strike Earth's atmosphere, they ionize atoms and molecules, creating showers of secondary particles. Some scientists propose that this ionization influences cloud formation, potentially affecting weather and climate patterns. Though the exact impact remains debated, cosmic rays represent a link between distant energetic processes in the universe and Earth's atmospheric behavior. This connection reminds us how intertwined our planet is with the cosmos. What happens in a supernova explosion thousands of light years away might subtly influence the weather outside your window. It's all connected. The Big Bang should have produced equal amounts of matter and antimatter, which annihilate each other upon contact. Yet our universe is overwhelmingly made of matter, with antimatter nearly absent. This imbalance, known as the baryon asymmetry, puzzles scientists deeply. It suggests that some unknown processes in the early universe favored matter's survival. Understanding this mystery is crucial for explaining why anything exists at all, from galaxies and stars to planets and life. It remains one of the most profound unanswered questions in physics and cosmology. Why is there something rather than nothing? Why did matter win out over antimatter? These questions keep scientists awake at night, searching for answers in particle accelerators and cosmic observations. As light travels through the universe, it passes near massive objects like galaxies and clusters, whose gravity bends and distorts its path, a phenomenon called gravitational lensing. These subtle shifts imprint tiny distortions on the cosmic microwave background radiation, the oldest light we can detect. By studying these distortions, astronomers can map the distribution of both visible and dark matter. Gravitational lensing offers a powerful tool to understand the universe's structure and the invisible forces shaping it. Massive celestial bodies act like cosmic magnifying glasses, warping space and bending light, creating arcs, rings, or multiple images of distant objects. This natural magnification enables astronomers to observe galaxies otherwise too faint or distant, revealing the hidden structure of the universe. After hundreds of millions of years of darkness following the Big Bang, the universe's first stars ignited, ushering in the era of cosmic dawn. These pioneering stars grouped into early galaxies, their collective glow piercing the darkness and filling the cosmos with light for the very first time. This ancient light marked a fundamental transformation, the end of the cosmic dark ages, and set in motion processes that led to the complex cosmic structures we see today. This first illumination laid the foundation for the growth of galaxies, star clusters, and eventually planets, offering the universe its first glimpse of brilliance. Imagine that moment, the first photons streaming outward into the void, lighting up space for the first time in hundreds of millions of years. It must have been spectacular. In the universe's early years, space was filled with neutral hydrogen gas that absorbed much of the light trying to travel through it, making the cosmos foggy and opaque. The formation of the first stars and galaxies changed this. Their ultraviolet radiation ionized the surrounding hydrogen atoms, stripping electrons away and turning the gas into plasma. This re-ionization phase cleared the cosmic fog, allowing light to stream freely across space. This transformation from opaque to transparent opened a window for the universe to shine clearly, enabling the vast cosmic web of galaxies to emerge and be observed billions of years later. Without reionization, we wouldn't see the universe as we do today. It would be hidden behind a veil of neutral gas, dark and unknowable. Billions of years ago, the universe experienced a period of intense star formation, often called cosmic high noon or cosmic noon. During this epoch, galaxies were rapidly creating stars at rates much higher than we see today. This surge in star birth enriched the universe with heavier elements, essential for planets and life. Gas was plentiful, collisions between galaxies were more common, and conditions were ripe for stellar nurseries to flourish. After this peak, star formation gradually declined, leading to the more peaceful cosmos we observe now. This golden age shaped the universe's evolution, weaving the fabric of matter that supports galaxies, solar systems, and ultimately life itself. We're living in the aftermath of that cosmic boom, in a quieter, more mature universe. The universe's earliest elements were mostly hydrogen and helium, products of the Big Bang. However, as stars formed and aged, they fused these light elements into heavier ones, like carbon, oxygen, and iron within their cores through nuclear fusion. When massive stars exploded as supernovae, they scattered these heavier elements into space, enriching the interstellar medium. This cosmic recycling allowed subsequent generations of stars and planets to form from richer material, eventually creating the building blocks necessary for complex chemistry and life. Over billions of years, the universe transformed from a simple primordial soup of hydrogen and helium into a chemically diverse environment where carbon-based life could emerge. Every atom in your body heavier than hydrogen was forged in the heart of a star or in a supernova explosion. You're literally made of star stuff. The large-scale structure of the universe resembles a vast web, with clusters of galaxies linked by enormous filaments of matter stretching millions of light years. These filaments, composed mainly of dark matter and gas, form the backbone of the cosmos, guiding the movement and growth of galaxies. Between these threads lie vast voids, immense regions of empty space. This cosmic web shapes how galaxies cluster and evolve, revealing the universe's intricate architecture. Mapping these filaments helps scientists understand the distribution of matter and the forces shaping the cosmos over time. It's beautiful, really, how organized the universe is on the largest scales, how chaos and randomness give way to structure and pattern when you zoom out far enough. At the centers of many galaxies lie supermassive black holes, some of which unleash jets of charged particles traveling at nearly the speed of light. These jets can extend for millions of light years, affecting the gas and dust in their host galaxies. By heating and pushing away material, they regulate star formation and influence the galaxy's evolution. These energetic outflows can prevent gas from cooling and forming new stars, or sometimes trigger bursts of star formation by compressing gas clouds. Observing these jets reveals the dynamic relationship between black holes and their cosmic environments, showcasing some of the universe's most powerful phenomena. Despite being invisible themselves, black holes have a profound and visible impact on their surroundings. Galaxy clusters are the universe's largest gravitationally bound structures, containing hundreds or even thousands of galaxies packed into regions millions of light years across. These clusters act as the densest nodes within the vast cosmic web, where filaments of dark matter and gas intersect. The immense gravity in clusters pulls galaxies together, influencing their motions, interactions, and evolution. These regions are also filled with hot gas that emits X-rays, adding to their dynamic complexity. Studying galaxy clusters reveal how matter is distributed on the largest scales and offers clues about dark matter, dark energy, and the universe's history. They're like cosmic cities, bustling with activity, galaxies interacting and evolving in close proximity. Cosmological measurements show the universe's geometry is astonishingly flat, meaning it doesn't curve inward like a sphere or outward like a saddle. This flatness implies a precise balance between the universe's total energy and its expansion rate. A flat universe means parallel lines stay parallel, even over cosmic distances, shaping the paths of light and matter. This discovery supports inflationary models that predict such geometry and helps determine the universe's ultimate fate, suggesting it will expand forever rather than collapse. Understanding the universe's shape is key to unraveling cosmic evolution. It's remarkable how finely balanced everything is, how the universe sits right on the edge between different geometrical possibilities. The cosmic microwave background radiation appears nearly uniform, but contains minute temperature fluctuations, variations of just a few millionths of a degree. These tiny ripples represent slight differences in density in the early universe. Over billions of years, gravity amplified these small variations, causing matter to clump and form galaxies, clusters, and the large-scale cosmic web. These ancient fluctuations are essentially the universe's original blueprint, dictating how cosmic structures grew and evolved. Mapping them provides a window into the universe's infancy and the fundamental physics at play. Without these tiny imperfections, the universe would be completely uniform, and galaxies, stars, planets, and life would never have formed. We owe our existence to those microscopic ripples in the fabric of spacetime. Cosmic variance is a fundamental limitation in cosmology, resulting from having access to just one universe. Since we can only observe our unique cosmic environment, statistical studies of galaxy distributions or cosmic background fluctuations carry inherent uncertainties. Without multiple universes to compare, we cannot be certain whether observed patterns are universal or just chance occurrences in our particular cosmic neighborhood. This uncertainty challenges astronomers to develop sophisticated models and careful analyses to ensure robust conclusions. Cosmic variance reminds us of the unique vantage point and limits of our cosmic knowledge. It's humbling, knowing that some questions might be fundamentally unanswerable because we only have one universe to study. Astronomers use the light from distant galaxies to estimate their ages, effectively looking back in time. By analyzing stellar populations and spectra, scientists determine how long ago these galaxies formed stars and what their histories look like. Since light takes billions of years to reach us, observing distant galaxies reveals the universe's history across epochs. These age estimates help build a timeline of cosmic events, tracking galaxy formation, star formation rates, and chemical evolution. Together with other observations, measuring galaxy ages paints a detailed picture of how the cosmos grew from its earliest moments to the rich structures we see today. Each galaxy's light is a time capsule, carrying information about when and how it formed. Cosmic strings are theoretical one-dimensional defects in spacetime, predicted by some early universe physics models. Imagine ultra-thin, immensely dense filaments stretching across the cosmos, formed during phase transitions fractions of a second after the Big Bang. These strings, if they exist, could produce gravitational waves or cause distortions in the cosmic microwave background. Detecting cosmic strings would offer profound insights into fundamental physics and the conditions of the infant universe. Though no direct evidence has yet been found, cosmic strings remain a fascinating possibility in cosmology, linking quantum physics to cosmic structure. They're like wrinkles in the fabric of spacetime itself, remnants of the universe's violent birth. Deep within many galaxies lurk supermassive black holes, often millions or billions of times the mass of our sun. When these cosmic giants actively consume surrounding gas and dust, the material forms a swirling accretion disk, heated to millions of degrees by friction and gravity. This extreme environment emits powerful X-rays that shine across billions of light years, detectable by space telescopes. These X-rays reveal violent processes occurring near the black hole's event horizon and help astronomers understand black hole growth, their energetic feedback on galaxies, and the role they play in shaping cosmic evolution. Observing these glowing beacons provides a window into some of the universe's most extreme and mysterious regions. Within galaxies, vast clouds of gas churn turbulently, stirred by gravity, shockwaves from supernova, and magnetic forces. This turbulence compresses parts of the clouds, triggering the collapse of dense pockets that ignite as new stars. The balance between turbulence and gravity controls how many stars form and how massive they become. This intricate dance of chaotic motions and gentle collapses governs the life cycle of galaxies. Understanding this turbulence is key to unraveling how galaxies evolve and sustain star formation over billions of years. Star formation isn't a smooth, orderly process, but a chaotic, turbulent one. Beauty emerging from chaos. Pulsars, which are rapidly spinning neutron stars left behind after massive star explosions, emit beams of radio waves sweeping through space like cosmic lighthouses. Alongside pulsars, many galaxies emit diffuse radio waves from energetic processes like star formation and black hole jets. Radio astronomy captures these signals, revealing hidden aspects of the universe invisible in visible light. These radio waves allow scientists to study exotic objects, map magnetic fields, and explore the large-scale structure of the cosmos. Listening to this invisible radio symphony offers insights into the universe's energetic and dynamic nature. The universe is singing to us in wavelengths we can't see, but we've learned to listen. When massive stars end their lives in supernova explosions, they unleash shockwaves that accelerate particles, mostly protons and atomic nuclei, to near light speed, creating cosmic rays. These energetic particles traverse the galaxy, occasionally colliding with Earth's atmosphere and producing cascades of secondary particles detectable by instruments. Cosmic rays influence the chemistry and dynamics of the interstellar medium, and possibly Earth's atmosphere. Their origins and properties connect Earth to distant violent cosmic events, serving as messengers from some of the universe's most energetic phenomena. Every cosmic ray that strikes Earth carries with it the signature of a stellar explosion or other cataclysmic event from somewhere in the galaxy. The cosmic microwave background radiation, the afterglow of the Big Bang, not only shines faintly, but also exhibits polarization, where light waves oscillate preferentially in certain directions. This subtle polarization encodes information about gravitational waves and density fluctuations from the universe's earliest moments. By studying these patterns, scientists test theories of cosmic inflation and understand how tiny quantum ripples evolved into the large-scale structures of galaxies and clusters. These delicate signals offer a unique glimpse into the physics of the universe's birth and the forces shaping its evolution. Polarization is like a fingerprint, revealing details about conditions in the first moments after creation. After the first stars formed, their intense ultraviolet light ionized the surrounding hydrogen gas that had made the early universe opaque. This process, called reionization, stripped electrons from hydrogen atoms, transforming the cosmos from a foggy, light-absorbing haze into a transparent expanse where photons could travel freely. This fundamental change allowed light to journey vast distances, revealing galaxies and structures billions of years later. Reionization marks a key transition in cosmic history, opening the universe's windows and shaping its evolution toward the star-filled sky we observe today. The universe went from being cloudy to clear, like fog lifting on a morning landscape, revealing the view beneath.
As the universe emerged from darkness, the first galaxies ignited intense ultraviolet light that ionized surrounding hydrogen gas. This ionization stripped electrons from hydrogen atoms, changing the universe from a neutral, foggy state into a transparent one. This process, known as reionization, allowed light to travel freely across space for the first time, illuminating the cosmos and revealing the large-scale structure of galaxies. The ionizing power of these early galaxies transformed the universe's appearance and marked a major milestone in cosmic evolution. Studying this transition helps scientists understand how the first luminous objects shaped the universe and paved the way for the complex structures we observe today. Though gravity pulls matter together, a surprising discovery revealed that the universe's expansion is accelerating, driven by an enigmatic force called dark energy. This dark energy acts like a repulsive pressure, pushing galaxies apart faster over time, accounting for about 70% of the universe's total energy content. Dark energy remains one of science's greatest mysteries. Its nature, origin, and ultimate effects on cosmic fate challenge our understanding of physics. Whether dark energy will cause endless expansion, remain constant, or change over time remains unknown. Unraveling its secrets is a central quest in modern cosmology. It's unsettling and exciting at the same time, knowing there's this invisible force pushing the universe apart and we don't understand it at all. Cosmologists use the scale factor to track how space itself stretches as the universe grows. This dimensionless number changes with time, describing the relative expansion since the Big Bang. When the scale factor doubles, distances between galaxies also roughly double, illustrating cosmic growth. Measuring its changes helps scientists understand the universe's expansion history, the influence of dark energy, and the dynamics of cosmic acceleration. The scale factor provides a simple yet powerful way to chart the vast unfolding of the cosmos over billions of years. It's like a ruler for measuring the universe's growth, a single number that captures the entire expansion history. The universe's geometry, whether flat, open, or closed, depends on its total density of matter and energy. A flat universe means parallel lines stay parallel at cosmic scales, implying a balance between gravity and expansion. If the universe were curved like a sphere, it might eventually collapse back on itself. If curved like a saddle, it would expand forever, becoming increasingly sparse. Current observations show the universe is astonishingly close to flat, shaping our understanding of cosmic evolution. This curvature influences the universe's fate and the paths of light and matter, guiding the grand cosmic journey. The shape of space itself determines what happens in the far future. When viewed on scales spanning hundreds of millions of light years, matter, including galaxies and dark matter, is remarkably uniform.
This homogeneity means that statistically, no region is significantly denser or emptier than another on the largest scales. This even distribution simplifies cosmological models and supports the cosmological principle, which assumes the universe is isotropic and homogeneous. Though locally galaxies cluster and voids exist, the overall cosmic balance reveals fundamental symmetries and structures that govern the universe's evolution. It's like zooming out from a pointillist painting. Up close, you see individual dots, but step back far enough and the overall pattern emerges, smooth and uniform. Cosmic isotropy means that the universe appears almost identical no matter where we look. Observations, including those of the cosmic microwave background, show uniform temperature and matter distribution across the sky. This isotropy, together with homogeneity, forms the foundation for modern cosmology's understanding of the universe's large-scale structure. It suggests that the laws of physics and cosmic conditions are consistent throughout space, allowing scientists to develop universal models describing cosmic history, expansion, and evolution. There's no special direction, no cosmic preferred orientation. The universe treats all directions equally, which is both comforting and profound. In 1965, scientists Arno Penzias and Robert Wilson accidentally discovered a faint, uniform microwave glow permeating the universe, now known as the cosmic microwave background radiation. This ancient light is the afterglow of the Big Bang, dating back nearly 14 billion years to when the universe first became transparent. Its discovery provided powerful evidence supporting the Big Bang theory, transforming cosmology from speculation to science. Detailed measurements of this radiation revealed tiny temperature fluctuations that seeded the formation of galaxies and large-scale structures. The cosmic microwave background remains a cornerstone of our understanding, acting as a time capsule from the universe's infancy and a guide to its evolution. It's everywhere, filling every corner of space, a whisper from the beginning of time. The universe's story began in an unimaginably brief instant, the Planck epoch, just a fraction of a second after the Big Bang. From this fiery birth, cosmic history unfolded through epochs: inflation, nucleosynthesis, recombination, cosmic dawn, and galaxy formation. Each stage brought profound changes: space expanding, matter cooling, light emerging, and structures forming. Billions of years passed as galaxies evolved, stars ignited, and planets took shape. This vast timeline reveals a universe in constant transformation, where every moment connects past, present, and future in an ongoing cosmic dance. Understanding this timeline helps us grasp our place in the grand scheme, as late arrivals in a universe that's been evolving for nearly 14 billion years. The observable universe is bounded by the cosmic light horizon, the farthest distance from which light has reached us since the Big Bang. As time passes, this horizon slowly expands, allowing us to see more distant galaxies and structures. However, due to cosmic expansion, some regions may remain forever beyond our reach, receding faster than light can travel to us. This expanding horizon represents the limits of human observation and knowledge. It's a reminder that while we've seen incredible cosmic depths, much of the universe still lies hidden in darkness, waiting patiently for future discoveries and expanding our sense of wonder. Gamma ray bursts are intense flashes of high-energy radiation that briefly outshine entire galaxies. These bursts, lasting from milliseconds to minutes, often result from massive star collapses or merging neutron stars. Despite their fleeting nature, gamma ray bursts release tremendous energy, illuminating distant corners of the universe. They serve as cosmic beacons, providing clues about stellar death, black hole formation, and the universe's evolution. Observing these brief, powerful events allows scientists to probe extreme physics under conditions impossible to repeat on Earth. For a few seconds, a gamma ray burst can be the brightest thing in the universe. Then it fades, leaving only the memory of its incredible flash. As the universe expands, light waves traveling through space are stretched, increasing their wavelength, a phenomenon known as cosmological redshift. This stretching shifts light toward the red end of the spectrum, making distant galaxies appear redder than they actually emit. Redshift serves as a cosmic clock, allowing astronomers to measure how fast galaxies recede and to estimate their distances. This effect provides direct evidence for the universe's expansion and enables us to look back in time, observing galaxies as they were billions of years ago. The stretching of light is a subtle but profound signature of cosmic growth, written into every photon traveling through expanding space.
Almost immediately after the Big Bang, the universe was filled with relic neutrinos, tiny, nearly massless particles that rarely interact with matter. These neutrinos decoupled from the hot plasma within 1 second, streaming through space ever since. Though incredibly difficult to detect due to their weak interactions, relic neutrinos influence cosmic evolution and the formation of large-scale structures. They represent a cosmic fossil, carrying information about conditions in the universe's earliest moments. Detecting and studying these neutrinos remains a major goal in physics, promising insights into the universe's fundamental nature. They're out there right now, billions upon billions of them, passing through everything, silent witnesses to the Big Bang. Cosmic voids are vast, sparsely populated regions stretching millions of light years across, where few galaxies or matter exist. These immense voids are like cosmic deserts, contrasting sharply with dense galaxy clusters and filaments. Though nearly empty, voids play a crucial role in shaping the universe's large-scale structure by influencing the gravitational pull and motion of surrounding galaxies. Studying voids helps scientists understand the distribution of dark matter, the effects of dark energy, and the overall evolution of cosmic architecture. These silent expanses remind us of the universe's vastness and the intricate balance between matter and emptiness. Space isn't just filled with things, it's also defined by the absence of things. Galaxies are dynamic entities that grow and evolve by merging with neighbors. These galactic mergers are slow, majestic processes unfolding over billions of years, during which stars, gas, and dark matter combine. Mergers can trigger bursts of star formation, reshape galactic structures, and fuel central black holes. Our own Milky Way is expected to collide and merge with the nearby Andromeda galaxy in several billion years, creating a new, larger galaxy. Understanding galaxy mergers reveals how cosmic structures build up complexity over time, painting a picture of a universe in constant transformation. Nothing in the universe is permanent. Even galaxies change and grow over cosmic timescales. Magnetic fields, though invisible, permeate galaxies and influence cosmic processes. These fields guide the motion of charged particles, affect star formation, and shape the behavior of interstellar gas. Though weak compared to Earth's magnetic field, galactic magnetic fields stretch over thousands of light years, weaving through spiral arms and galactic halos. Studying these magnetic forces help astronomers understand the dynamics of galaxies, the propagation of cosmic rays, and the interplay between matter and energy on grand scales. These unseen threads add complexity to the cosmic tapestry, invisible forces shaping visible structures. Cosmic rays are energetic particles originating from supernovae and other cosmic phenomena. When they strike Earth's atmosphere, they create showers of secondary particles that reach the surface. Some of these particles penetrate living organisms, occasionally causing mutations in DNA. While most mutations are harmless or repaired by cellular mechanisms, some contribute to genetic variation and evolution over long timescales. The constant rain of cosmic rays links Earth's biological history to the broader universe, illustrating how cosmic phenomena subtly influence life on our planet. Evolution itself is partly driven by cosmic events, by particles from dying stars changing the genetic code of life on Earth. In the universe's earliest moments, rapid changes called phase transitions may have created bubble-like structures in spacetime. These bubbles, expanding and colliding, could have left imprints on the cosmic microwave background or produced gravitational waves. Such phase transitions relate to fundamental forces separating and symmetries breaking as the universe cooled from its initial extreme heat. Detecting evidence of these bubbles would provide insight into high-energy physics and the conditions just after the Big Bang, offering a glimpse into the universe's fiery birth. These hypothetical structures represent moments when the laws of physics themselves changed, when forces unified in the early universe separated into the distinct forces we see today. The cosmic microwave background radiation carries faint ripples, tiny temperature and density fluctuations that are the seeds of all cosmic structures. These subtle variations represent slight differences in matter concentration in the early universe, which gravity amplified over billions of years into galaxies, clusters, and cosmic filaments. By mapping these fluctuations with exquisite precision, scientists decode the universe's initial conditions and test cosmological models. These delicate imprints offer a profound window into the universe's origins and the forces shaping its evolution. Every galaxy, every star, every planet exists because of those tiny ripples in the ancient light. The dazzling auroras, northern and southern lights, are partly sparked by cosmic rays, high-energy particles traveling through space. When these particles collide with Earth's magnetic field and atmosphere near the poles, they excite gases, causing them to glow in vivid colors of green, red, and purple. Cosmic rays, along with solar wind particles, energize the upper atmosphere, creating these mesmerizing light shows. This cosmic connection between distant energetic events and Earth's skies reminds us that our planet is part of a vast, dynamic universe, with subtle cosmic influences shaping natural wonders. Those beautiful lights dancing across polar skies are caused by particles from the sun and beyond, painting the atmosphere with energy from space. Galaxies don't drift randomly, but move along vast gravitational currents defined by the universe's distribution of matter, especially dark matter. These invisible flows guide galaxies along filaments of the cosmic web, pulling them toward dense clusters and away from voids. This cosmic dance shapes galaxy formation, interactions, and evolution over billions of years. Understanding these gravitational streams help astronomers map the large-scale structure of the universe and uncover the forces driving cosmic evolution, revealing the interconnectedness of matter on grand scales. Everything is flowing, moving along invisible rivers of gravity that channel galaxies through space. Approximately 380,000 years after the Big Bang, the universe cooled enough for photons, particles of light, to decouple from matter and travel freely. This event, called recombination, marks the release of the cosmic microwave background radiation, the oldest light visible today. Before this, the universe was opaque, with photons constantly interacting with charged particles, scattering endlessly. The moment of last scattering transformed the universe into a transparent expanse, allowing light to journey across space and time. Studying this light reveals the universe's early conditions and its evolving structure. It's the moment the universe became see-through, when light could finally escape and travel freely. The cosmic microwave background radiation is nearly uniform, but contains tiny temperature differences, mere millions of a degree. These small fluctuations correspond to density variations in the early universe. Over billions of years, gravity amplified these differences, leading matter to clump and form galaxies, clusters, and the cosmic web. These primordial seeds set the stage for the universe's large-scale structure. By precisely mapping these temperature variations, scientists gain insight into the universe's infancy and the forces that shaped its evolution. Those tiny differences, almost nothing, grew into everything we see, the entire cosmic structure emerging from microscopic variations.
Just as the moon's gravity influences Earth's tides, gravitational forces from nearby galaxies and dark matter create tidal effects in galaxies themselves. These gravitational tides stretch, distort, and reshape galaxies, affecting their spiral arms and star formation patterns. Over millions of years, tidal interactions can trigger bursts of starbirth or even lead to galactic mergers. Understanding these tidal forces reveals how galaxies evolve within their cosmic neighborhoods and highlights the dynamic, interconnected nature of the universe. Galaxies pull on each other, stretching and warping each other's shapes across the vast distances of space. During a brief period of cosmic inflation just after the Big Bang, tiny quantum fluctuations, minute variations in energy, were rapidly stretched to cosmic scales. These fluctuations became the seeds from which all galaxies and clusters grew. Inflation magnified these tiny ripples, imprinting them onto the fabric of space-time. Over billions of years, gravity amplified these variations, forming the rich cosmic structures observed today. This remarkable process links the quantum realm to the vastness of the universe, revealing the profound interconnectedness of nature's smallest and largest scales. The smallest possible things, quantum fluctuations, became the largest structures, galaxies and clusters, through cosmic inflation. Tiny grains of cosmic dust, composed of elements like carbon, silicon, and metals, drift through interstellar space, playing a vital role in the universe's life cycle. These dust particles gather in vast clouds, cooling the gas and enabling it to collapse under gravity. This collapse sparks the birth of new stars, while the surrounding dust coalesces into disks that can form planets, moons, and other celestial bodies. Dust also facilitates complex chemical reactions, creating molecules essential for life. Though minuscule, these cosmic grains are the building blocks of stars, planets, and ultimately the rich tapestry of the cosmos. Everything solid in the universe started as tiny dust grains floating in space. A light year is the distance light travels in 1 year, about 6 trillion miles or 10 trillion kilometers, offering a convenient way to measure cosmic distances. Using light years, astronomers can describe how far away stars, galaxies, and other celestial objects are, helping us grasp the immense scale of the universe. For example, the nearest star beyond our sun is over 4 light years away, meaning its light takes more than 4 years to reach us. When we look at that star, we're seeing it as it was over 4 years ago. Light years provide a sense of cosmic time and distance, linking the vastness of space to the speed of light's journey. Every astronomical observation is also a journey into the past. The cosmic microwave background radiation, the universe's oldest light, permeates all space with a chilling temperature of about 2.7 degrees above absolute zero. This faint glow is the cooled remnant of the hot, dense early universe, stretched and cooled as space expanded over billions of years. Its near uniform temperature carries tiny fluctuations that seeded cosmic structures. The cold temperature highlights how the universe has evolved from a fiery beginning to its current vast, cool state, embodying the passage of cosmic time in a silent, pervasive glow. The universe has cooled down, aged, matured from a blazing inferno to a cold expanse, dotted with islands of warmth like stars. When high-energy cosmic rays, particles traveling near light speed, strike Earth's atmosphere, they collide with atoms, creating cascades of secondary particles called air showers. These showers spread through the atmosphere, sometimes reaching Earth's surface, detected by instruments worldwide. Cosmic ray showers provide insights into the universe's most energetic processes, like supernova and black hole jets. They also interact with atmospheric chemistry and possibly influence climate patterns. Constantly raining down, cosmic rays remind us of Earth's connection to the broader cosmic environment. We're being constantly bombarded by particles from space, most of which we never notice. Cosmic voids, vast regions with few galaxies, impact the dynamics of nearby galaxies and clusters. Their low density creates gravitational effects that push surrounding matter outward, influencing the flow and clustering of galaxies. Voids shape the cosmic web's evolution, guiding matter along filaments and affecting galaxy formation and interaction. Studying voids help astronomers understand dark energy's role and the universe's large-scale structure. These empty expanses, though seemingly barren, play a subtle but crucial role in cosmic evolution. The absence of matter has just as much influence as the presence of matter in shaping the universe. Supermassive black holes at galaxy centers often emit powerful jets of charged particles traveling near light speed. These jets can extend millions of light years, influencing their surroundings by heating and dispersing gas. By regulating star formation and reshaping the interstellar medium, black hole jets act as cosmic sculptors, affecting the growth and evolution of their host galaxies. Observing these jets offers insight into the interplay between black holes and galaxies, revealing dynamic processes shaping the universe's grand design. Black holes aren't just destroyers, they're also architects, shaping the galaxies around them. Cosmic dawn represents one of the most transformative epochs in the universe's history, the moment when the first galaxies ignited after hundreds of millions of years of darkness. During this period, primordial clouds of gas collapsed under gravity, giving birth to the earliest groups of stars and galaxies. These fledgling galaxies flooded the universe with ultraviolet light, initiating processes like reionization that transformed the cosmic landscape. This dawn marked the end of the cosmic dark ages and began the universe's luminous chapter. Studying this era reveals how the simplest building blocks evolved into the complex cosmic structures that fill the sky today, offering a glimpse into the universe's awakening from its initial silence. And now the cosmos is beginning to feel softer, more distant. You've traveled through almost 14 billion years of history, from the first fraction of a second after creation to the present moment. You've seen how matter clumped and spread, how light filled the darkness, how structures emerged from chaos. You've learned about forces we can see and forces we can't, about particles too small to imagine and structures too fast to comprehend. And through it all, one truth remains: you're part of this story. Every atom in your body, every breath you take, connects you to events that happened billions of years ago and light years away. The universe continues its patient unfolding, expanding moment by moment, galaxies drifting apart, stars being born and dying, planets forming and fading. Somewhere out there, light from distant galaxies is beginning its journey toward Earth, light that won't arrive for millions or billions of years, carrying stories of worlds we can't yet imagine. And here you are, right now, a conscious being made of stardust, thinking about the cosmos that created you, wondering about your place in it all. There's something deeply peaceful about understanding how vast and old the universe is. Your worries, your concerns, they're real and they matter to you, but they're also incredibly small in the context of cosmic time and space. There's freedom in that realization, comfort in knowing you're part of something so much larger than yourself, something that's been evolving and changing for nearly 14 billion years and will continue long after you're gone. You don't have to carry the weight of the universe on your shoulders. You're just here, now, for a brief moment, watching the stars, thinking about infinity, breathing quietly in the dark. So let yourself rest now. Let the cosmos continue its dance without your attention for a while. The galaxies will keep spinning, the stars will keep shining, cosmic rays will keep streaming through space, and dark energy will keep pushing the universe apart. It's all happening, all the time, whether you're watching or not. And that means you can close your eyes, let your mind grow quiet, let your body relax completely. You've learned enough for one night. You've traveled far enough. It's time to simply be, to exist peacefully in this moment, connected to everything, part of the cosmic story, but not responsible for telling it right now. Thank you for spending this time with me. Let me know in the comments where you're watching from and what time it is for you right now. I love hearing from all of you. This is Alara, signing off from the Late Night Science Channel. Sleep well, fellow traveler, wherever and whenever you are.